Okay, I want to talk about the history of calculus. In my paper, I talked about the history of calculus before Gottfried Leibniz, but this is going to focus mostly on Leibniz because he's one of the two founding fathers of calculus. It's a 3 to 5 minute video, so he's very important to calculus. He moved to Paris to do work in the field of math in the 1670s, and in 1675 he published a paper that was very instrumental to calculus, and even today. And it talks about the various rules of differentiation. So the first one is dA equals 0, which is the derivative of a, which is a constant, equaling 0. We know that. The derivative of v plus or minus y is equal to v dv plus or minus dy. The third rule, d of vw, you'll notice is the product rule. It's v dw plus it's just plus. v dw plus w dv. And the fourth one is d of v over y, which you might recognize as the quotient rule, which is plus or minus v dy minus or plus y dv all over y squared. And so where v, w, and y are all variables. And as you'll notice, they're not written in the exact same way that we see them today. You know, here for the quotient rule, he's got the plus or minus. But they all do hold true. They do all are ones that we use today in calculus, which is goes to show just how important he is that over 300 years later, we're still using his rules. Now in 1684, he published another paper. This one might be even more important. He talked about the power rule, the rule for roots, and he explained why differentials were so important. They help you find the local minima and maxima of functions, which is very important even in everyday life. And so he included a problem in it that I wanted to do as a practice problem. And so z equals g squared plus y squared. And you take the square root of that. And he wants to find the derivative of z. And so g is a constant, y is also another variable. So first he sets r equal to the part inside the square root. The derivative of r is equal to, because this is a constant, it's just 2y dy. Now we go back to the function z equals root r, dz is equal to d root r, dz is equal to, now this is the rule of roots. So you move 1/2 to the front and you do r to the negative 1/2. And then you plug in, and so you get dz is equal to 2y dy all over 2z. The 2's cancel out, and he ends up with dz equals y dy over z. And if we did this today, we would probably do it slightly differently. We wouldn't use the r substitution, which is similar to the u substitution, actually. We would go straight to the rule of roots. So we do it more efficiently today than we would then. But it's not that different, and we get the same answer either way, which goes to show, the rules that he used today, or that we used back then, are still very important today. And in 1694, he published a third paper, he's done more papers than that, but a third important paper talking about integration, and it talked about creating an organized form for integration. And so he's basically the father of both differentiation and integration, which are the two most important tenets of calculus. And integration is important because it helps find areas and volumes of different shapes and functions, which, as you can tell, is also important for real-world functions. And so he's incredibly important to the history of calculus. His work in the late 1600s helped set up future mathematicians for their work in calculus, and everything that was done after that has built off his basic principles. As you can see, based on this problem and his rules here, we still use a lot of what he did today from what he did back in the day. Thank you.